Hello, everyone. Welcome to the last talk of the day and the last talk of the conference. We have today Mike Haworth, a pen tester for Aura Info Security. He's previously talked at NZ OWASP and at KiwiCon, which you may have heard of, and if you haven't, you've now heard of it, and you should come because KiwiCon is awesome. It will be in December. Python is his tool of choice for doing, things that he probably shouldn't talk about in the world of penetration testing and security. And he's here today to tell us about surprise features in Python that we probably didn't ask for.
Cool.
Mike.
Thanks for that intro. Cheers. So yeah, the theme of my talk is surprise features that you didn't ask for. So it's a talk about web application security, but it's outside of things you might find in the usual, OWASP top 10 type issues. And my talk is kind of inspired by, I saw Tom Eastman's talk. He talked about problems with serialization formats and all the horrible things that can go wrong with that. So it kind of builds on that kind of idea that you have all this functionality in these libraries and the stack that you're using, and they can often they are very feature rich and they have features that can really bite you. So there's going to be three main things I'm going to talk about. The first one is server-side request forgery. The second is Mischief with serialization, and I stole Tom's slides for that bit, so thanks, Tom. Cheers. And the last bit is problems that can happen with signed cookies. So server-side request forgery, this is when you have an application, web application, and it's making requests on behalf of the user, and that can be misused. So simple example is we have a simple form that will test our API. The user provides the URL, the application server goes and makes the request to some other host, and it displays a response to the user. So it's pretty straightforward. Here's that in action. The user submits the request, the server sends off the HTTP request, and the response comes back and it's displayed back to the user. Simple stuff. How can that go wrong? So here's a bottle app that implements that functionality. We just take the URL parameter that's sent in the post from the user. We make a new request object. We go out and make that request, and we take the response from that and we send it back to the user. So here's how it can go wrong. We ask our web application to look at localhost on the MongoDB port, and our web application dutifully goes and talks to the MongoDB host and sends us back the admin page. Fantastic. So problems with server-side request forgery. That previous example demonstrates, we can access these services that are running on localhost, so there's no authentication. You can just straight talk to them. Often in a web application, there's going to be multiple servers, database server, cache server, whatever, and we can potentially talk to those other hosts that are in the DMZ that we wouldn't otherwise be able to talk to because of the firewall or NAT or whatever's in the way. And we can also potentially bypass host-based restrictions. So we've seen applications that we test where there'll be the front end, and the front end will talk to some middleware, and that middleware may have an API that's completely unauthenticated, and the only security there is that, hey, if it's coming from this application server, then I trust it, and whatever it asks for, I'm just going to give it, so you can bypass authorization doing that. So yeah, there's a bunch of examples that use host-based authentication where there's no actual username, password, or other means of authentication. It just trusts where it's coming from. So there's Memcache. Docker has an interesting REST API where it has a feature that's kind of analogous to shared folders in VirtualBox, so you can map the host root file system to some location on a guest. So that could potentially be misused if you have access to the Docker host. It's not enabled by default, but again, it's an unauthenticated API. Mongo has an unauthenticated API, CouchDB, and I'm sure there's a bunch more. So how this impacts if you're using Python. So urllib3 and requests libraries, and requests just uses urllib3. They can you can whatever. This slide's actually wrong. It says that you can only forward a HTTP GET, but if it's making a GET request, you're stuck with the GET. You can't change that because you're only able to control the URL at that point. URL and URL2 and PyCon all support the file handler or scheme, and so you can read local files from these, which it comes as a bit of a surprise. So here's an example. This is the same bottle app as before. We're just using URL2, and we just straight up go, hey, can I have Etsy password? Thank you very much. So that's kind of a surprise feature that you might not have anticipated. A reasonable person would expect the app to behave that way. Speaking of unreasonable, PyCon accepts the Gopher protocol, at least it did for me on Ubuntu 14.04. So Gopher, like what even is Gopher? Like it's a HTTP text-based protocol. I've honestly never used Gopher except to do this. So and you can literally construct like arbitrary packets using Gopher. So if an application is using PyCon, you can start making arbitrary packets and send them all around their internal network. So here's an example where we're forging a post request. So again, we are talking to our web application. It allows us to put an arbitrary URL. There's some other host on that network, on the internal network, that accepts post requests. It's an API that allows us to add users, for example. And if we know what that endpoint is, we can merely send it, hey, add me as a user, add the user hacksaw to this host. So another way this can be abused is memcache, right? So memcache is a key value store that interacting with it speaks a plain text protocol. If you're just doing the admin interaction, you can just telnet to memcache and start storing key value pairs. So here's a sample of like an interaction with memcache. Here we're going set my key, and the value of my key is my data. And then we can get it back. We can just go get my key and we get our data back. So with our trusty Gopher protocol, we can like read arbitrary stuff out of memcache. So this is, if this was in a real application, this could be quite a devastating attack, because you're going to bypass all authorization checks, because memcache is just key value, it doesn't really care. And if you're able to do that as, say, an unauthenticated user, you could read data that belongs to authenticated users. So the other potential problem with this is in Django. Does anyone know how Django stores stuff in memcache? Like it pickles data and then puts it on memcache, right? So if you can write to memcache and then have Django execute it back off, then there's going to be a bunch of problems with that. So I thought there's a pen tester bug bounty guy who made his own kind of bug bounty to try and demonstrate problems with server-side request forgery, and to write a wrapper for curl to make it less vulnerable to server-side request forgery. And I thought this illustrates quite a few good examples of how tricky a problem this is. When you're allowing, if you're in a position where you have to allow a user to make a request to an arbitrary location, how tricky it is to actually prevent this from coming unstuck. So in the setup, he's got his Bitcoin private key that's sitting in a text file on his server. He sets an htaccess file. In this htaccess file, it says, I'm only going to allow a request to this file if it comes from me, if it comes from my server. So allow from 127.0.0.1 and the public IP of that server. Otherwise, 403, you can't touch it. So examples of bypasses here. The first bypass is the request was just made to 0.0.0. So normally in web applications, I guess that reference means like listen on all interfaces. But in this instance, curl merely just kind of sends that request to localhost, and away we go. And so here's another example of a bypass where there's kind of one of these impedance mismatch problems. So he's doing some initial sanitization to do the blacklisting by using parse URL from PHP. And then curl is receiving the URL. So the parse URL is saying, hey, that looks like that request headed off to Google, and curl is saying, no, I think it's heading to the local host. So preventing server-side request forgery is actually kind of a tricky business. You have to block requests to private ranges. You have to allow the request to the current IP, so there's some configuration required there. And if you are whitelisting based on the protocol, if you're saying, oh, I only want you to make HTTP requests, but the underlying library is able to do file : / then you can have a problem. So I liked this this particular bug. If you read this, some smart ass basically found an issue in the WC3 HTML validator. You know how this works. You put in the URL to your website. Press go, it makes a request to your site, parses the HTML and tells you all the trivial errors that you have made. So this wise guy has basically said, well, I pointed your feed validator at my website, and my website has a redirect on it. That redirect issues a 302, pointing to file : / and then the feed validator displays the content of its Etsy password. And you think, oh, well, that's pretty ridiculous. When did this happen? Yeah. So, yeah, that's a bit embarrassing. So I guess this is just to illustrate that that this is it's a tricky problem to solve, and pretty much everyone has this kind of problem. So the next section of the talk is about kind of mischief that can go on with serialization formats, and basically this is just me whinging about problems with XML. So XML is literally everywhere, isn't it? It's like RSS, SVG, document formats, image formats, APIs that you deal with. Even if you don't want to deal with it somewhere, some other part of something that you need to do is dealing with XML. I mean, there's very few people who go out of their way and go, right, I'm going to use XML for everything. It's so awesome. So here's the slide I stole from Tom. Thanks again, Tom. So again, we're just sending some XML to our server. We're using LXML, which is a popular Python XML parsing library, to parse the XML, and we're just displaying the result back to the user. So this is an example of an XML entity. All an XML entity is where we have you can think of it like variable substitution. In this instance, there's an entity called author, and it just replaces instances of author with the string John Doe. So when we submit that XML to the server, we just get an XML document back with our root tags and then John Doe, because it's done the replacement for us. So the way to abuse that, I'm sure a lot of you will have seen this before, the billion laughs attack is a well-known kind of abuse of XML entities. So, and it's done by virtue of chaining all of these entity expansions together. So you can see that that is exponentially, first lol is string lol, second lol is a whole bunch of those first entities, and the third one is a whole bunch of the previous, etc. And it just, it's going to exponentially ramp up and consume memory. And so that's how this is done. It's basically a denial of service attack. The server runs out of memory and things stop happening. So the other, somebody in their infinite wisdom, when they designed the XML spec, thought, what would be really awesome is we would like to have entities that reference external files. That'd be super. So for whatever reason, this exists, and now we can read arbitrary files off the server. So in pen testing, we find this with surprising regularity, believe it or not. And some of the stuff that people store on their web servers is, you would not believe it. Like, obviously, you can read application code. There is a limitation with this technique in that if the file has stuff that is going to muck up the XML parser, then you might not get the content back. So generally, it's like plain text file is going to be okay, but every time there's like angle brackets, then it's going to get it may not parse. So yeah, I mean, we've found things like SSH private keys without passwords, Amazon S3 keys, all kinds of stuff that is just it certainly makes the pen test more entertaining. So this has got nothing to do with Python. But I thought I'd put it in anyway because it's more like a, This affects Java on Windows. So this is like, thank God I'm using Python and I'm not using Java on Windows. So this attack works where we're making a reference to an external entity. That entity is a Windows share. So what we do is we say to the host we're attacking, we're saying, hey, I've got a Windows share, you should totally check it out. The machine we're attacking makes a connection back to us, and we do SMB relay. So the way SMB relay works is we can, if someone makes a connection to us, we can pass those credentials on to somebody else and use those to own that box. So we tell the victim, hey, you should totally come and check out this file that we've got for you. You take the credentials that the victim sends to you, you send them to somebody else, and you use that to run code on that other machine. So I was able to use this in a pen test, and yep, that was fun. So in order to illustrate that problems with XML aren't just limited to external entities, there's also a problem with DTD retrieval. So you can say, so this affects the SAX parser. Basically, the short version of that is this slide is similar to LXML, doing the same thing. We're taking content from the user, parsing it. So here we are submitting our XML document to the server. We're defining external DTD. That external DTD is on the attacker's server. And then here's us listening with NickCare, and there's the incoming connection from the host that's parsing the XML. So this table is a pretty good summary of all the problems with the various XML parsers in Python. It's pretty much an advertising campaign by the guy who writes Diffuse XML. So he's saying, essentially saying, these XML libraries, they got problems. And you should totally use Diffuse XML because this is a bit of a minefield. And the ones I've highlighted there are the ones that tend to be the most annoying sort of problem that you can have, which is where you can read a local file. So if you can include external entities, you're going to be able to read a local file. There's also another one called like X-include, which can allow inclusion of local files. So what's this got to do with Python and Django? I guess Django, popular way of getting an API for Django is to use TastyPy. So I think it was early 2013 that the TastyPy developers realized that they were vulnerable to XXE and other XML problems, so they switched to using Diffuse XML. So the short version of problems with parsing XML is that if you are accepting XML from users, basically the best bet is to use Diffuse XML. But most people don't really choose to parse XML as something that kind of happens, or you're using some third-party library that's doing it for you, or you've got to parse some arcane document format that you don't really want to have to deal with, and you use some third-party code to do that. So the other thing is to look at the third-party code that you're using, because it may be doing something with the XML under the hood, and it might not be doing it in a safe way. So this is the last part, and I'm going to cover problems with signed cookies. So there's kind of, what I mean by signed cookies is there's kind of two ways of doing session management, right? You can have a cookie that has a random token in it, and that random token is mapped to a state on the server where there's an object that represents the user's session and all the stuff that's going on with the user. The other technique, popularized I guess by Rails and other like minimal Python frameworks, is that you can actually just offload that task to the client. You can serialize the client's state, the user's state, and actually store that in the cookie directly. And the trick there is that the mechanism by which that is done is it's always signed. So there's a server-side secret, and that server-side secret, what we do is we hash that object, and we hash it with a server-side secret, so that if the client tries to forge an object and send it to us, we know that it's been tampered with, because we know the secret and we can tell that it's been forged, which is all well and good. So one of the issues with signed cookies is that the content of that cookie is visible to the user, which is all well and good, but it depends what you store in it, right? Like and you're storing stuff about what the client's up to. So my colleague Matthew Daly found this in a recent pen test, is like the application was storing the two-factor challenge that it was about to send to you in the cookie. So two-factor bypassed straight up. So the next one is, well, we trust this data that's coming from the user, so we can do stuff based on it, right? So what if there's like a discount that's being applied to that user, says, hey, give me 10% discount? Well, we can just replay that. We can just go, oh, give me 10% discount again, give me 10% discount again. So the protection against that, right, is you have a nonce, like a number only used once. You keep adding that inside the session, and you can, if there's an attempt to reuse that number, you can drop that attempt. So it's totally okay to deserialize any content from the user. What could go wrong with that, right? Because the only way anyone could ever know that key is if they have access to our server. Well, what if there's other vulnerabilities with these applications? There could be other ways to read that key. So different frameworks use different approaches to serializing this data. So with JSON, we've got problems with the content being visible to the user. We've got potentially problems with replay attacks. And if the secret is known by the attacker, then they can potentially change the content. But with pickle, it's a bit different. So we've got all of the above, plus we've got the risk that unpickling that user data introduces a risk of remote code execution. So I know that problems with pickle is pretty well-worn security topic with Python, right? But I thought I might just step through the mechanism by how that works, because it kind of helps with the example I'm going to illustrate in a minute. So here's a script that will make a new exploit object. It will print out, it will serialize that exploit object, and it will print it out, and then it will reinstantiate that object from the serialized string. So we can define a reduce method. This reduce method basically just says, hey, here's some code that you're going to run when that method gets instantiated, when that object gets instantiated. So here we're making the new exploit object, we're serializing it. Now we're printing out the object that's been serialized, and we can see that there's this pickle stack language. Basically, you can think of it as assembly code for the Python VM. We're not really too concerned about what that looks like, because we can do this next part, which is when we instantiate the object, we've defined this reduce method. In the reduce method, it says, hey, use OS system and run this command touch pwned into temp. So we run our script, it dumps out some object code, we check temp for this file pwned, and hey, it's there, so our code ran. So with using pickle, these frameworks have started to give up on using pickle for this fairly obvious reason. So Django, since 1.6, has been using JSON. Flask switched to JSON in 2013. My personal favourite, It's Dangerous, which is the best named library ever, defaults to using JSON, but pickle is still optional. So frameworks that still use pickle is Bottle, Pylons, Wurtzug, and Beaker. So I'm going to demonstrate how this can come unstuck in Bottle, but I haven't tested it in the other ones. I just went in GitHub and looked how they're serializing cookies, and hey, that looks like pickle to me. But so they may or may not be vulnerable to remote code execution. I haven't personally tested them. So here's the cookie decode function from Bottle. You can see, hey, it's just doing pickle load s. It's just instantiating whatever's come out of that cookie. So steps to get remote code execution are, we need to read the secret off the server. We need to write some code that gives ourselves a shell. We need to use pickle to serialize that code. We need to base64 encode that pickle code, and we need to sign it with that key that we stole off the server. And then we send the cookie to the application, and it will dutifully run whatever code we gave it. So here's our little bottle app that we made. Log in with admin. What else? So the app greets us with, hey, I've got an XML API, you should come and check it out. And plus it gives us the hint of, here's the location of the secret. So in practice, you have to kind of muck around and guess where that secret is stored. So we are reading, here we're using XXE to read the file. We know it's this bottle.secret file, and it's got the most awesome secret key of military grade crypto. So here's some code for the remote shell. Essentially all this is doing is it's saying, hey, make a connection to, open a socket and connect to attacker.com and hook up binsh to that socket. So we get interactive shell. So we've done, the first two are on 3, which is we're going to serialize our reverse shell code. So we just create an object with a reduce method that will execute that shell code. And here we've kind of just glued it all together. We've got a script shell that does all of the above. We pass it the secret. It creates the cookie with the signature. So that second part, the first part is the signature, and the rest is the payload. That's just so it's base64 and it's pickled, but it's code that will run that reverse shell to connect back to us. So we're listening on port 1234, and the server makes a connection back to us, and we can just ls, and we can see the content of that current directory. So that's the end of my talk. We're hiring. If you like the sound of doing pen testing, there's some pen test challenges at this URL. It'll fire up EC2 instance. There's like binary reverse engineering. There's also like a memory corruption challenge, and there's a bunch of web application challenges as well. So come check that out if you're interested. Cool. Thank you for your time. Cheers.
Thank you very much, Mike. That was really interesting. Do we have any questions? I'm seeing no.
Is it beer time yet?
Just about. I think we have closing remarks from Tom and or Jen in a couple of minutes. So if you just hang in your seats, we'll let the other session come in.